everyone. I'm Amrit from SEM1, and today I'm going to explain the work I did at my summer training at CDAC Noida. So I interned at CDAC Noida in the machine learning department during my summer, and I worked on a very interesting utility which is meant to take the meter reading, extract the meter reading and meter number from an image of a gas meter and push it to a server or something where it can be utilized. So basically it's an automated meter reader. Today there's a lot of applications of these automatic meter readers because they save a lot of time, they increase transparency, billing accuracy, etc. So let's get started. I wrote the code using a few libraries such as OpenCV and Tesseract, which is an optical character recognition engine by Google. So taking the input from the command line. Here, 1.py is the file name in which my code is contained, and gas1.jpg is the image of the meter from which the meter number and the meter reading is to be extracted. So this is what happens. The meter number, which is this, and the meter reading, which is this, is extracted from the image of the meter, which I can show you. Yeah, this is the image of the meter. And this meter number is extracted from this part, and the meter reading is extracted from this part, and this is done by applying various image processing and feature extraction algorithms which are contained in the OpenCV library, which I'll explain after some time. And this is what happens. The meter number is outputted, which is 100% accurate, 31490591, 31490591, and the meter reading is also given as output, which is 00449 and two gibberish characters after that. Actually, the fact is we only need the five most significant figures of the meter, because the last three the least three significant figures are not even noted by the people who come to take your meter reading, because they change very quickly in the matter of a few hours. So they are interested in the five most significant digits which are correct in the output. So yeah, so let's move on to the algorithm. Sorry, the code is a bit cluttered because I was doing some research work with this. Yeah, so the code is written in Python using various libraries such as OpenCV, NumPy for fast, quick mathematical calculations, because images are represented in the form of matrices which actually involve very heavy calculations, but this library has all those matrix calculations and operations very highly optimized and quick. Matplotlib, which is used to plot these matrices into images, and PyTesseract, which is a which is optical character recognition engine by Google. So the first step is obviously to take the input, the image as an input. The then the image is converted to grayscale, because we can't easily work with color image because it has three layers, which is red, green and blue. It is comparatively easier to work with grayscale or binary images. Then of course it is easier to work with grayscale images, binary images, sorry. That's why we convert the grayscale image to a binary image in this step. Now the two arguments 100 and 255 are very interesting here. 255 is the both of these are actually intensity values of the pixel. Now the grayscale image which we have is an 8-bit image, so there are 0 to 255 pixel intensity values available. So the first parameter is, which I have given to be 100, is the pixel value. If is the pixel intensity value. If the pixel intensity value is above 100, then it will convert it to 255, and if if it is below 100, then it will convert it into 0. So basically 0 and 255 are white and black. So this image sets a threshold which is 100 here, and according to the threshold divides the intensity values into two, black and white, and thus the image becomes a black and white image from a grayscale image, which is far more easier to deal with than a grayscale image. Then in this step we just take out the dimensions of the image. Now this step is very interesting and very important because contrast stretch, we need contrast stretching. An image can be clicked in various lighting conditions, and the most common noise is there is no there's not much contrast in the image. So to if you want if if you want the OCR engine to recognize the digits accurately, then the image contrast should be high. So what this function of the OpenCV library does is it equalizes the histogram of the image. An histogram is a bar graph which gives an information about the intensity and how many pixels have that particular intensity value in an image. So basically what this does is it stretches the histogram towards left and right the such that more pixels have a varied intensity values. So what this results in is a contrast stretching and an enhanced contrast. Now that we have a binary image with good contrast between black and white, now what we want to do is detect some edges and find the contours, because we want to extract the probable region of the meter number and meter reading. So what this function of the OpenCV library does is that it finds contours. What finds contours, yeah. So the principle behind this is canny edge detection. In canny edge detection, the first of all the iterator moves from left to right and detects various gradients along the x direction. Then it does the same along the y direction, and wherever the gradient intensity value at whatever pixel is the highest, that pixel is deemed to be an edge, and continuous edges are deemed to be contours. So in this function, in uh, in the in the list img contours, all the contours pixels are stored as various lists. Now what we want to do is we want to detect the enclosing rectangle of the meter number and the meter reading. So what we do is we iterate on the contours, and this function of the OpenCV library finds the bounding rectangle. The bounding rectangle encloses the meter number. To ensure that we are extracting the meter number and not any other rectangle, we make use of the aspect ratio. Aspect ratio is the ratio of the width and the height. So, and another factor which we make use to ensure that the meter number is being extracted or enclosed by the rectangle is white count. White count is basically the ratio of white pixels versus total pixel of the white pixels versus total pixels. So yeah, using these two and some error margins, we put a condition that if the aspect ratio is around 8.355 and the ratio of white count lies between 0.1 and 0.45, then we are sure that the bounding rectangle is enclosing the meter number region. And what we do is extract that part of the whole meter image and store it in another variable called ROI, which is region of interest meter. Now we have the meter number extracted. So what we want to do is we just store it for the while, because now we want to extract the meter number. Earlier we were extracting the meter reading. So what we do is again follow the same procedure. We take the whole image, convert it into grayscale, then we apply a bilateral filter here. As we know, the meter number region is far smaller than the meter reading, which means that it has a lower resolution, so the chances of edge detection are very low. So what we want to do is we want to maintain we want to remove the noise without uh, you know unsharpening the edges. So this is what a bilateral filter does. A bilateral filter is basically a noise removal transform which keeps the edges sharp. So we apply this on the meter. Now again we apply thresholding, but here we use a different thresholding technique called adaptive threshold. Now this threshold doesn't use a common threshold. This image binarization technique doesn't use a common threshold value for the whole image. It iterates along the image in few regions whose size is defined in using these parameters, and for each region it calculates a threshold, a separate threshold, and according to the threshold binarizes the image. So this results in a better and more high contrast binary image. Then again we use a median blur to remove noises. Now we what as the text of the meter reading is very small, and it can we want the bounding rectangle to be enclosed properly. So what we do is we create a kernel, elliptic kernel, and move it along the region. That is, we want to dilate it so that it becomes as bold and wide as possible, so that the enclosing contour can be detected as a rectangle. Now these steps here are for used for extracting the meter number region. In the whole image we have some idea by doing research on a lot of images about the position of the meter number with respect to meter reading. We already have extracted the meter reading, so now we want to extract the meter number. So what we do is we take some relative ratios and extract a probable region of the meter number using these some calculations. So again we want we use an elliptic kernel to erode now, because earlier we had dilated the image to make it bold. Now we want to erode it so that the size and the widths of the various text characters return to original. Again we repeat the same process. We find the contours, we find the bounding rectangles, we use white count and ratios as deciding factor if the rectangle actually does contain the meter number or not. Again we do thresholding. So yeah, now we move on to segmentation. The next important part of recognizing characters from images is segmentation of characters in a continuous string of texts. So we already had extracted a meter number region, so now we want to segment the meter. So again what we do is we use a technique of blob detection, which is finding the contours and drawing the bounding rectangles over the contours. So here the bounding rectangles are drawn on each character, that is each digit in the meter number, which is stored in a list called W. Now what we do is we after each bounding rectangle over digit we create a line. The line signifies the extraction or the cropping of each digit from the whole meter number region, and each of these digits is stored in again as a separate image. After all this, the images are fed to PyTesseract, which is a optical character recognition engine by Google, which is a highly optimized and trained OCR engine, which can detect and extract or read characters and numbers from images. So we feed both the extracted images of the meter number and meter reading to PyTesseract, and what it gives is number and reading as text. The last part is outputting everything, printing the meter number and the meter reading. So again showing the same thing. This is the meter number, the meter reading, and this is the output. Meter number is 31490591, meter reading is this. Now the problem with detecting meter reading is because the meter reading part is in black color and is slightly in the backward part of the meter. So in clicking pictures, that part is enclosed by a glass screen, so a glare usually comes out. So to increase the accuracy of this reading, we need a lot of meter images to train our own neural network, which is the future work part of this project. I've already contacted my mentor at CDAC to provide me with good images and a lot of at least 1,000 meter IGL meter gas meter images, so that I can train my neural network and build and work more on it, so that this utility can become more optimum, and more further expansions can be done, such as, this whole algorithm can be made into an API which can be called from an Android app, and this app can be given to various lo- the clerks and people representatives of IGL, who can go from home to home, just click the pictures of the meter, and the meter reading and the meter number will be read from using the algorithm, and will be pushed to the servers of IGL, from where billing can be done easily. Thank you very much.